Duff's and Marley Bridge replacements over Dingo Creek. The project was initiated to replace two aging single-lane Allen timber truss bridges, requiring detailed site investigation, innovative engineering solutions, and rigorous project management to complete two three-span, two-lane concrete bridges, culminating in opening ceremonies in November 2012 for the Duff's Bridge and April 2013 for the Marley Bridge. The process began with an options report and extensive site investigations in May 2011. To streamline construction and demolition, nearly identical bridge designs were developed for both Duff's and Marley, despite different site and roadway constraints. The designs incorporated variable size spans to accommodate hydrological requirements and avoided existing piers, ensuring compatibility with the 5- and 6-span configurations of the original structures. This standardization allowed for economies of scale, simplified construction processes, and allowed for innovative solutions. Foundation design, recommended by regional GE Technical Solutions, utilized permanently cased large-diameter board piles, penetrating 3 meters into bedrock to mitigate scour risks from Dingo Creek's fast-flowing waters. Each bridge featured 2 pile piers, positioned on either side of the existing timber decks, eliminating the need to pile through the decks and enhancing safety by reducing work around live traffic. The steel-encased concrete piles extended to headstock level, supporting precast concrete headstocks and deck planks. This approach minimized construction time in the waterway, reducing exposure to flood risks and work at heights, critical given the creek's history of flooding. Site preparation involved constructing crane pads, installing temporary support structures, and organizing storage for precast components including deck planks, headstocks, and curtain walls. The demolition of the timber truss bridges posed significant challenges due to their poor condition and unpredictable structural behavior. For Duff's Bridge, standing over 16 meters high, a 500-ton all-terrain crane, the largest feasible for the constrained site, was employed. Demolition required an unrestricted demolition license from work cover due to the height. During a 10-day closure, the bridge was closed to traffic in the early morning, and each span was lifted using the crane, lowered to ground level, and disassembled to minimize work at heights. The limited site area necessitated crane standby periods while spans were disassembled, a process later optimized at Marley. At Marley Bridge, an innovative temporary support structure was erected beneath the timber truss span, providing stability and a safe working platform. The 500-ton crane, reconfigured to 350 tons due to capacity limitations, removed the span in 2 sections. The identical bridge designs allowed reuse of the same steel support structure, reducing costs and safety risks. The new piers were ingeniously designed to incorporate temporary steelwork supports, eliminating the need for additional substructure supports and minimizing the risk of machinery damage during installation and removal. At Marley, a 60-ton crane removed end principals and diagonals to access new piers for steel headstock installation. Delaney Civil, leveraging experience from Duff's, obtained a restricted demolition license and performed the demolition, as Marley's height was only 8 meters. The construction phase utilized precast concrete planks with transverse post-tensioning bars, enabling immediate trafficability and significantly reducing closure durations. Edge planks were fitted with pre-attached scaffolding, providing safe access for installing transverse bars. A 200-ton crane, positioned on the opposite bank, lifted planks for the far span, using small hydraulic jacks and specially fabricated steel blocks inserted into plank attachment holes for precise alignment. A trial assembly of precast planks in Brisbane prior to delivery identified and rectified issues, such as misaligned transverse bar holes, preventing costly delays during closures. The transverse post-tensioning system employed the Dividag DCP system, featuring pre-grouted bars and corrugated PVC sheaths with a smooth PVC skin for double corrosion protection. These bars were inserted as complete units with a 45 mm thick bearing plate and nut for anchorages. Planks were pulled together with a 100 kilonewtons load, and cement grout was poured into joints, curing for 18 hours. The bars were then released and retensioned to 350 kilonewtons, eliminating secondary grouting and enhancing long-term corrosion resistance. This system allowed for future maintenance, as bars could be restressed or replaced if needed. Barrier rails were pre-attached to edge planks, with remaining sections pre-assembled and installed on site. All ferrules for scaffolding and formwork were cast in place and capped for corrosion protection, ensuring future maintenance access. Precast abutment headstocks and curtain walls were installed quickly to further reduce closure times. At Duff's, headstocks were installed before closure, as the existing truss span was higher than the new design level. At Marley, the truss deck required removal first, extending the closure process. Duff's Bridge opened in November 2012, on the 7th day of its 10-day closure, 5 months ahead of schedule. Marley Bridge used the full 10-day closure in April 2013 due to headstock and deck installation requirements. 2 flood events in early 2013 delayed Marley's closure, but effective project management and minimal waterway work mitigated impacts, maintaining the schedule and budget. Time-lapse photography from Duff's informed Marley's demolition, reducing crane standby time and improving efficiency. Sound timbers from the demolished bridges were reclaimed for other council assets, and the temporary steel structure was designed for potential reuse as an emergency crossing, enhancing sustainability. The project's success hinged on innovative solutions, such as standardized designs, precast components, and the Dividag system, combined with rigorous planning and continuous improvement. The use of existing alignments, despite initial challenges, minimized closure durations and costs, delivering high-quality, durable infrastructure that supports 44-ton trucks and 68-ton B-doubles, enhancing safety and economic viability for the community. Construction of the Mississippi Bridge began in 2011 to replace ferry crossings over the Adaturk Dam lake. After blasting 150,000 cubic meters of rock, foundations for the 96-meter-high inverted Y-shaped pylons were prepared. Each pylon was built using 31,000 cubic meters of high-strength concrete and 4,200 tons of rebar. Due to the seismic nature of the region, the structure was designed to withstand a 2,475-year return period earthquake. Approximately 6,500 tons of steel were prefabricated in Osmanier, transported in 250-ton segments, and assembled on-site. Some segments were floated across the reservoir on barges, then lifted using heavy lifting equipment specially designed by Turkish engineers. Each segment was connected with extensive welding over 712 kilometers in total and supported by tension cables. 80 cables, each formed from strands of steel wire, anchored the segments to the pylons and approach bridges. When water levels dropped unexpectedly, engineers extended a floating beam by 17 meters to reach deeper water and avoid delays. Temperature changes and structural displacement were monitored continuously, and assembly was adjusted accordingly. Finally, after nearly 3 years of work, the last 6-meter segment was lifted and placed, completing Turkey's longest-span cable-stayed bridge built entirely with domestic resources. The construction of a Berkel precast concrete basement involves a highly industrialized and precision-controlled process. Wall and ceiling elements are manufactured in a fully automated carousel system at one of the most advanced precast facilities in Europe. Using CAD/CAM integration, robotic shuttering systems form the molds with millimeter precision. Reinforcement steel is automatically cut, bent, and placed into position according to structural engineering specifications. Robotic arms ensure accurate placement and anchoring of rebar within each panel. Integrated components, such as electrical conduit boxes, piping sleeves, and other embedded parts are positioned using laser-guided systems to match the project layout. High-performance waterproof concrete is dispensed and compacted using computer-controlled vibratory tables, ensuring optimal consolidation, eliminating air pockets, and producing smooth, defect-free surfaces. This precision eliminates the need for post-processing like plastering. After curing under controlled conditions, the elements are demolded, quality inspected, and loaded for just-in-time delivery to the construction site. At the site, Berkel's construction crew begins by casting the waterproof base slab using water-impermeable concrete. After curing, the layout of wall panels is set out using laser surveying instruments. Wall elements are lifted into place with cranes, aligned with 1 mm tolerance, and temporarily braced with steel diagonal props and corner brackets. Following wall installation, precast ceiling slabs are hoisted and positioned. These slabs feature embedded channels for MEP, mechanical, electrical, and plumbing installations. Immediately after slab placement, reinforcement meshes and electrical conduits are installed on top of the ceiling panels. A monolithic structural connection is achieved by pouring in situ concrete over the joints and slab surfaces. The result is a highly durable, structurally integrated, and watertight basement system. Berkel guarantees 100% structural integrity and waterproofing for 10 years. The final structure complies with seismic design codes and supports advanced thermal insulation systems, including the Climatech solution for enhanced moisture control, energy efficiency, and acoustic insulation. This method ensures dimensional accuracy, minimized construction time, and long-term performance of the basement structure. During Christmas 2011, a major railway bridge replacement project got underway at Cow Lane in Reading. The new 1,600-ton concrete and steel bridge was pre-built at a nearby site to minimize disruption. Cranes lifted and placed large precast concrete beams onto the newly constructed piers. Workers secured them in place and continued assembling the deck components. Formwork and additional reinforcing bars were added before the concrete was poured to complete the bridge deck. Once the concrete had set, bitumen was applied to the bridge, and waterproofing was applied. The bridge edges were finished with guardrails and safety barriers. Drainage was also installed during this phase. Precast concrete components and steel reinforcement were also delivered and assembled on site. The old bridge was demolished overnight so that the new bridge structure could be transported to the site on Tuesday morning by a 66-axle self-propelled modular transporter. The massive vehicle moved slowly and carefully, guided by engineers and supervisors to ensure proper alignment. Next, the construction team installed sheet piles to support the earthworks. A major excavation was conducted to create the foundation area for the new bridge structure. Then, the concrete footings and piers that form the bridge's base were poured. The new bridge was moved and installed in place and replaced the old bridge. In parallel with the bridge construction, the rail infrastructure was upgraded. The tracks were raised and replaced to align with the new bridge. Signaling equipment and overhead lines were adjusted and reconnected. The 61.75-meter-long girders were transported in reverse over a 3 kilometers work road through the fields from Rasdorp Junction. Upon arrival, they waited on a pontoon in the Ringvaart. Two 700-ton cranes then lifted and placed the girders onto the structure at KW 511. The placement process spanned 3 days, from March 16 to 18, 2011, during which all 25 girders were accurately positioned. The replacement of Bellside Bridge began with the design by AECOM and temporary works by MHB. The new bridge structure was fabricated nearby in Lanark over 8 weeks before being transported to site. A site compound was established at the old Cleland station, allowing construction of working platforms and crane pads. A road closure on the A73 enabled 5 weeks of preparation, including building platforms and a system of trestles to support the new bridge. The 260-ton structure, consisting of 2 cell units and 2 EU decks, was assembled and welded on-site. A 650-ton crane lifted the components into place for welding and grouting. A self-propelled modular transporter with a rotating tower crane was assembled and used for the first time in UK bridge works to rotate the structure 360 degrees within the compound. During a 54-hour rail blockade, tracks and ballast were removed. The old bridge was extracted using the transporter and lifted out by a 500-ton crane. The abutments were demolished and prepared for the new installation. The new structure was then driven on the SPMT down the closed road and rotated into position. Final works included backfilling and track reinstatement. The line reopened successfully with only 11 minutes to spare. The new bridge now provides a 5.2 meters clearance, eliminating its low bridge status. The overpass construction begins with assembling the launching gantry on site. Temporary supports and guide rails are installed to align the structure. Precast concrete segments are delivered and positioned near the pier. The gantry then lifts the first segment using a winch and trolley system, carefully aligning it above the piers. Workers secure the segment with temporary post-tensioning bars. Subsequent segments are lifted and joined one by one using epoxy adhesive and tension cables. Each new segment is precisely aligned before tensioning is applied to form a rigid span. Once a full span is completed, the gantry moves forward by self-launching. It slides over the installed span onto the next set of piers using hydraulic systems. The cycle repeats for each span, with workers conducting constant checks for alignment, tensioning, and safety. After all spans are erected, permanent post-tensioning is applied, followed by removal of temporary supports. The process ensures rapid and safe construction, especially over roads or difficult terrain, minimizing disruptions to traffic below. The pipeline installation process involved the pullback of a 630 mm high-density polyethylene pipeline over a 347-meter alignment using horizontal directional drilling techniques. Prior to pullback, individual HDPE pipe segments were thermally fused using a butt fusion machine to create a single continuous length. The fusion process was executed under strict parameters for temperature, pressure, and cooling time, ensuring consistent joint strength and structural integrity. Once the pipeline string was assembled, it was positioned on a series of pipe rollers to facilitate smooth movement and minimize drag during pullback. The rollers were strategically spaced along the alignment to support the pipe, prevent sagging, and reduce surface friction. Simultaneously, the HDD contractor completed the pilot bore and successive reaming passes to enlarge the borehole to a diameter suitable for accommodating the 630 mm pipe. A final cleaning pass was conducted to ensure the borehole was free of obstructions. Drilling fluid circulation was maintained throughout to stabilize the borehole and transport cuttings to the surface. The fused pipeline was connected to the drill string via a pulling head and swivel. The swivel prevented torque transfer to the pipe during pullback, while the pulling head was designed to evenly distribute tensile loads and prevent pipe deformation. A reamer was attached ahead of the pulling assembly to maintain the borehole diameter and assist with fluid flow. During pullback, the HDD rig applied continuous controlled tension to draw the pipeline into the borehole. Pulling loads and fluid pressures were constantly monitored in real time. Communication was maintained between the drill operator and ground crew to synchronize motion and address alignment issues. Pipe alignment was closely managed, with ground crews guiding the pipe and ensuring it remained centered in the bore path. Once the pipeline emerged at the exit pit, The pulling head was removed, and final inspection was conducted to verify pipe condition. The operation concluded with preparation for tie-in to the existing pipeline infrastructure. This HDD pullback process highlights the integration of precision engineering, fusion welding, and real-time monitoring to achieve a trenchless installation of large-diameter HDPE pipe. The Gomaco GP 2400 performs slipform paving with high precision and efficiency. The concrete is first distributed using a split auger system that allows independent control on both sides, ensuring consistent material flow in front of the mold. The Open Front 3100 series paving mold features 10 standard vibrators and 18 variable control circuits to consolidate the concrete. A vertical action tamper bar further compacts the mix. The mold includes split, pressure-compensated side plates, enabling smooth transitions from headers. Trailing stainless steel components finish the concrete slab surface. The machine moves slowly and smoothly with its design tractive system, critical for consistent slip forming. Its telescoping frame hydraulically extends to pave widths up to 16.5 feet without inserts. Equipped with G+ control system, the GP 2400 offers simple setup and monitoring. Rear steer and full 360 degrees operator visibility ensure accurate alignment along string lines or 3D guidance for each paving run. The installation process begins by connecting the pressure grouting machine to the drilling rig. A hollow steel rod is used as the drill rod and equipped with a rotary hammer. Drilling is performed using a rotary percussive method, while simultaneously injecting drilling mud, ensuring fluid flows back out of the hole. As the rod advances, it is extended with couplers. Once the desired depth is reached, the process switches to dynamic pressure grouting using a grout suspension. Grouting is performed through the hollow bar. After grouting is completed, the drilling machine is disassembled. Once the anchors and shotcrete facing have cured, excavation continues. This sequence is repeated, enabling step-by-step construction of a stable excavation shoring system. The installation of the supersized clamshell box culvert began with lifting and placing the precast concrete base sections using heavy-duty cranes. Each base unit, weighing over 35 tons, was installed in under 7 minutes thanks to the cantilever joint design. Once in place, workers applied mastic sealant and liquid grout to the groove of the base to ensure a watertight seal. After sealing, the top sections of the culvert were lifted directly from transport trucks and carefully positioned onto the base grooves. This streamlined process enabled rapid assembly. In just 4 days, over 2,640 tons of concrete culvert components were successfully installed. The final structure, upon completion, will span 76.6 meters, serving multiple functions including wildlife passage, water conveyance, and as a short-span bridge for highway traffic. The clamshell design allowed for quick, efficient placement, helping keep the 407 ETR extension project on schedule and within budget. The complex railway reconstruction process at Shorely, focusing on excavation, drainage, structural reinforcement, and replacement of key arch components. Initially, the railway track is removed to allow access to the site. Excavators lower the track bed in stages, removing ballast and subgrade materials to reduce the track level. Simultaneously, temporary haul roads and access routes are created to facilitate machinery movement. Following excavation, a new drainage system is installed along the track alignment to manage groundwater and prevent future subsidence. Trenches are dug, and perforated pipes are laid and backfilled with gravel to ensure proper water flow. Next, workers install steel piles at regular intervals along both sides of the corridor. These vertical steel elements are driven deep into the ground to support future wall anchoring and lateral load resistance. With the piles in place, the team installs ground anchors and wall tiebacks to stabilize the excavation. Drilling rigs bore holes into the sidewalls, and steel tendons are inserted and tensioned to secure the structure. The most significant phase involves the replacement of the original stone flying arches. Cranes and work crews dismantle the aging masonry arches and remove them from the site. In their place, prefabricated steel arches are carefully lifted and installed. These new steel arches are fixed to the foundation piles and anchored securely to the walls, providing both structural support and clearance for future electrification. After structural elements are complete, the subgrade is compacted, ballast is laid, and new railway tracks are installed. The entire process is executed efficiently to minimize disruption to train services, with precision coordination between excavation, structural work, and track reinstatement.